What you are about to see in this video might make you question the limits of what cosmology says should even be possible. Scientists just mapped the largest structure ever found in the universe, a structure so large that it stretches across a significant fraction of the observable universe. This is Hercules' Corona Borealis Great Wall, also known as her CRB, the largest candidate structure ever seen in the cosmos. And it's rewriting how astronomers think the universe organizes itself at the grandest scales. To understand how extraordinary this structure is, we need to start with how the universe is expected to look on the largest scales. Cosmology, the study of the universe as a whole, is built on one key idea: that on the largest possible scales, the universe should look roughly the same in every direction and location. Massive clusters and filaments can and do form, but their size should be limited by how quickly structures can grow under gravity in an expanding universe. Until most large structures were under a few billion light years across, impressive, but not shocking in light of theory. Then came Hercules' Corona Borealis. Unlike structures identified by directly mapping galaxies, Hercules' Corona Borealis was discovered by looking at gamma-ray bursts, GRBs, the brief, brilliant flashes that signal the collapse of massive stars or collisions of neutron stars. Because GRBs are so bright, they're visible even from billions of light years away. By measuring how far away these bursts are and where they appear in the sky, astronomers found something surprising. Many of them cluster together instead of being evenly spread out. This clustering suggests that thousands, maybe even billions of galaxies are gathered in this region, following the same giant structure. That means the pattern seen in these gamma-ray bursts is likely a clue to a real cosmic structure. Originally, the Hercules Corona Borealis Great Wall was estimated at about 10 billion light years in length, making it easily the largest known structure in the observable universe, far larger than earlier reported walls and filaments. More recent reanalyses of GRB data suggest this colossal feature might extend even farther, potentially up to 15 billion light years if its clustered regions truly belong to the same coherent structure. To put that in perspective, the observable universe has a diameter of roughly 93 billion light years. The Milky Way galaxy is about 100,000 light years across. Even massive superclusters like Laniakea span just hundreds of millions of light years. Hercules, Corona Borealis, dwarfs them all so large that light has taken billions of years to travel from one end to the other. Not everyone agrees. The trickiness lies in how Hercules' Corona Borealis was detected. Unlike filaments mapped directly through galaxy surveys where relationships between galaxies are visibly traced, the Great Wall is inferred indirectly through the spatial grouping of gamma-ray bursts. That makes it statistically significant. Studies show the clustering is unlikely to be a random fluctuation, but it's still debated whether the GRB clustering truly represents a single physical structure or a projection of several overlapping features in space and time. Even though scientists still debate whether the Great Wall is truly one connected structure, most agree on the main point. Matter in the universe is grouped on much larger scales than we used to think. On cosmic scales, matter doesn't spread evenly like dots on a balloon. It forms something that looks almost biological, a cosmic web. Nodes, dense clusters of galaxies. Filaments, strings of galaxy groups, and dark matter. Voids, vast emptiness between filaments. Everything is connected, like a giant, three-dimensional spiderweb of matter. Structures like the Sloan Great Wall, Perseus, Pegasus, Filament, and other superclusters were once considered huge, but the Hercules Corona Borealis Great Wall makes those look small by comparison. In that web, Hercules Corona Borealis might be the near-ultimate filament, a leviathan thread weaving across the universe's history. If a structure this large truly exists, it sits uncomfortably with the theory that on large enough scales, the universe should appear smooth and homogeneous. The Higgs inflationary theory and the standard picture of cosmic evolution all suggest that matter should only clump on scales up to about 1 billion plus light years before expansion smooths everything out. Yet her CRB sits at 10-15 billion light years, potentially violating that limit by an order of magnitude. That doesn't mean current physics is wrong, but it does suggest either. We need refinements in our models of structure formation. We need to understand how early universe fluctuations could grow into something this vast, or that our assumptions about homogeneity might need updating. Either way, this is the kind of discovery theorists live for when observation nudges theory to adapt. Another remarkable consequence of this discovery is when we see this structure, light from Hercules' corona borealis has taken about 10 billion years to reach us. That means we are seeing the structure as it was billions of years ago when the universe was less than half its current age. That gives us a window into the universe's adolescence, a snapshot of how matter was arranged when galaxies were still growing, colliding, and forming stars at a dramatically higher rate than today. Finding such a huge structure from that early time suggests that the building blocks of the universe were set up very early on, maybe during the inflation period, and managed to stay together through billions of years of change. Quipu and other superstructures. In addition to Hercules' corona borealis, astronomers have identified other massive features in the cosmic web. One of the most remarkable is Quipu, a filamentary superstructure spanning roughly 1.3 billion light-years, which was first introduced in a research paper posted on the 31st of January 2025. Quipu was mapped through conventional galaxy surveys and, while spectacular in its own right, is still dwarfed by the scale implied by Hercules' corona borealis. Other giant structures, like the Shapley supercluster, Serpens corona borealis, and Sculptor Pegasus filaments, also form part of this cosmic tapestry. Altogether, these discoveries show that gigantic filaments are more common than once thought, but Hercules' corona borealis remains the biggest contender in terms of sheer stretch across the cosmos. Large-scale structures don't just sit in space quietly. Their mass affects gravitational lensing, bending light from distant galaxies, like a warped magnifying glass. Cosmic microwave background measurements, subtly shifting early universe signals, local measurements of the Hubble constant, because regions dominated by massive structures don't expand at uniform rates. In regions dominated by superclusters and walls, galaxies are tugged by gravity, as well as cosmic expansion, which complicates precision cosmology. Understanding how these massive walls influence expansion and structure growth is vital if we hope to resolve current tensions in cosmology, like differences in the measured expansion rate of the universe from different methods. At first glance, structures spanning billions of light years might seem too abstract to touch daily life, but they matter because they test the assumptions underlying modern cosmology. They reveal how matter and energy behaved in the early universe. They show that the cosmos is less smooth and more dynamic than once thought. Most of all, they remind us of our cosmic address, a small galaxy within a modest supercluster. If you genuinely enjoy exploring the universe and its mysteries, consider subscribing. It helps us keep going. Better instruments are coming. The next generation of surveys and telescopes, like those mapping galaxies and GRBs in greater detail, will probe whether Hercules' corona borealis is truly coherent or whether its boundaries are more complex. Whether it's a single vast wall or a series of aligned filaments, future data will bring clarity. Seeing structures this vast puts human existence into perspective. From cities to continents, our scales are tiny. From planets to galaxies, we expand outward. But even galaxies are mere grains compared to the cosmic web we're mapping. Hercules' corona borealis isn't just a scientific curiosity. It's a reminder of the unimaginable scales the universe can organize itself on, and of how much we've learned and how much remains to be discovered. The Hercules corona borealis Great Wall is the ultimate cosmic giant, the largest candidate structure in the observable universe. It may span 10-15 billion light-years, traced by the clustering of gamma-ray bursts and possibly billions of galaxies. Structures like Quipu are impressive, but they're smaller compared to the sheer scale of this Great Wall. Whether it's ultimately confirmed in every detail or refined by future surveys, the existence of something this huge challenges how we understand cosmic structure, evolution, and the limits of the universe itself. If you could send a mission to map the universe's largest structures in even greater detail, what would you want it to discover next? Tell us in the comments. See you in the next video.